Okay, number 3 in our series of regression in RStudio. So this will be the 3rd video in our series. How many there eventually will be, who knows? We'll go until we've conquered it, until we cannot go anymore, as the saying goes. So we stopped. Okay, before I go there, thanks for joining. Thanks for watching. Thanks for your comments, your emails. Appreciate it, and we'll work on it. Yeah, for those that hasn't yet subscribed, yeah, please do so. Press those buttons. It's very straightforward, very easy, nothing to do. It doesn't cost you money. So please press those buttons. I really appreciate that. So where did we stop? We stopped at our regression. We generated a regression. And there it is. There's our regression. And we can, let me just confirm. I've got a space there. Let's just copy that one. I need to paste a couple of, let's see if I can delete this. There we go. I can delete this. So let's create a couple. Copy, paste, paste. Just a couple of them. Okay, so we can copy our results and we can paste it. And let's paste it. There we go. There's our results. Remember, we're looking specifically at our coefficients, because that's the important part. Now, that's the important part, is these coefficients. And what we want is we want these coefficients to be as accurate as possible. Is this coefficient really minus 3.382, or should it be something else? So the question mark is, where's my pencils? The question mark is this coefficient here. Is it really minus 3.382? Or should it, for example, be minus 4.2? What we do know, given these stars, is that it is not 0. So we know that it's not 0. But there's a hell of a lot of numbers beyond 0. 0 is one number of millions of numbers. So we know it's not 0. So for now, we're assuming that the value is indeed minus 3. We're assuming that. But it could be that this number is wrong. In fact, it rather should be minus 4.2. So that's important for us to look at. That's why we need to make sure that these coefficients are actually what they are supposed to be. They are minus 3.38. So by just looking at whether it's statistically significant or not, yes, that's important, but only in the sense that we can say it's not 0. But we're not testing whether it is actually minus 3.382. We're just testing whether it's 0 or not. And that's why that level of significance is indicating that. So that's a beginning. But now, is it minus 4.2 or is it minus 2.2? Is it overestimated? Is it overestimating or underestimating this coefficient? And that's why it's important that we do a whole lot of additional tests. Not to test whether this is 0 or not, but to test whether this number is true and robust. If it's not true and robust, then we have a problem in that we'll underestimate or overestimate. And you'll see when we get to that. This one we can already say is a no-go because it's not statistically significant. So in fact, that 1.0 is in fact 0. Is in fact 0. within this model. It could be that if we pair it with other variables, it might be statistically significant. But pairing wind speed with temperatures indicates that wind speed is in fact 0. Okay? So that's important. So by testing the statistical significance on these variables now, just indicates whether they're 0 or not 0. That's it. Big problem is this. Okay, so that's a big problem. It's very, very low. This is good. The F test is good. That is good. That is good. Okay. However, as I said, this is bad and that is bad. So there's some good stuff can be found in this. So it's not all bad. Some good stuff can be found, but some bad stuff as well. And therefore, this is pretty much in the working, in the making. This is not by all means a final product. Okay, so let's quickly have a look and see. Remember that we have an actual Y, and now we have a estimated Y. And the difference between the actual Y and the estimated Y is our error term. Okay. And so let's quickly have a look at our error term. So although we don't estimate our error term here, we can generate our error term. And then we can compare it with the actual, or well, we can generate our estimate using this coefficients. Using this coefficients, we can generate our estimate, and then we can subtract our estimate from the actual, and that will give us our error term. Okay, so let's quickly do that. So I can't do it in CSV. Remember, this is my CSV file. That's the CSV file that's in RStudio. So I don't want to hana with this. I don't want to work with this. So what I'm just going to do is I'm going to save this. Okay. I'm going to save it, same name. All I'm going to do is put it in an Excel spreadsheet and press save. Okay. Now this is now my Excel spreadsheet. So I've got two now. I've got my data sheet in CSV that I don't hana with. I don't change. I keep it as is because that's what RStudio is working on. But I've created a spreadsheet, an Excel spreadsheet. This is where I'm going to work with. Now the first thing that I have to do is get rid of all these dots, because dots are text. So I'm going to go to Find and Replace. What I'm looking for all the dots, and I want to replace it by commas. I'll replace all. It's 5,849, so that's a lot. Okay, so there's my stuff. So where's my Y variable? There's my Y variable. Okay, there's my Y variable. So I'm going to create now my estimate. Call it estimate. Okay. So how am I going to create my estimate? So first of all, I've got a constant, coefficient. I've got a max temp. Oops, sorry. I've got the max temp coefficient, and I've got a wind coefficient. So let's quickly just copy and paste those coefficients in there. And remember, these are dots, so I have to convert them into a comma. So that's my constant. And there's my maximum temperature. I'm going to correct them now. And there's my wind speed. So although this is not statistically significant, it's in the model, so I have to include it in calculating the estimate. So what I'm going to do, I'm just going to say find, replace all. It would only be 3. Oops, and there we go. So there's my actual participation for January 1960. So now what's our estimate? So our estimate is our coefficient plus our coefficient multiply our maximum temperature plus our wind speed coefficient multiplied our wind speed and enter. So that's my participation, and that is my estimate. So now I'm going to drag it down, okay? But before that, I need to just anchor my coefficients. So I'm going to anchor 0, 1. I'm going to anchor 0, 2, and I'm going to anchor 0, 3. Okay, if I don't anchor it, if I drag it down, these ones will also come down. So there we go. So take that for example. Yep, it's still on the anchored value. That's it. So there's my estimate. So what I can do, I can now plot the two. Okay, so let's plot them. Insert. And there it is. So let's cut it. Let's move it to the top. Paste it in there. And there it sits. Take that away. And there's our, and there's our graph. So our blue is the actual. Okay, so our blue is our actual, you can see. And the brown is our model. And you can see the model has a problem. It cannot predict rainfall outside a certain level. It cannot predict these rainfall. Call it high levels of rainfall. It can predict few rainfall, little rainfall, but it cannot predict these periods of high rainfall. It's good at predicting the low levels because it very seldom rains, so that's fine, but it cannot predict these rainfall, and that is actually the problem because we need the model to be able to predict this rainfall. Okay, so we can see there's quite a sizable error. Now we can calculate all sorts of statistics around this because what we can do is we can calculate the error, or we can generate the error term. Okay, we can generate the error term. The error term is simply the actual minus the estimate. That gives us the error term. So there's our error term. And we can also plot our error term. And there's our error term plot. Let's just take it up. And let's go and plot it just below this one. And there's our error term. Oopsie, sorry. And again, you can see it's struggling to predict these high values. The low values, the no rain values, it can fairly accurately predict. But these high rainfall periods, it's struggling to predict. So it's not very accurate in terms of the outlier. That's problematic because you will never be able to accurately predict or forecast these rainy periods. You will only predict it's not going to rain, not going to rain, not going to rain, not going to rain. So, let's see that. So we can change, let's say we do a -4 there. Let's see what happens now. And you can see if you put -4, you can see it's much lower now. You can see now it has all these zeros. So it's predicting all these minuses. So that's no good. So if we go -2, so now it's there, it diminishes there. You can see, so -3 seems to be somewhere in the middle. But you can see the influence of a small change in these parameters, in these coefficients on it. And that's really what the regression does. It estimates these so that it minimizes this error. It minimizes the error. So for example, let's say we actually need to square this first. So let's quickly do this, just for intersect. So equals power. Well, let's do absolute. absolute. Okay, let's just do an absolute. And then I'm going to say sum of the absolute deviations. Okay, so let's do that. Sum of the, we can do the mean of the absolute deviation, median, all sorts of things, but let's just do the sum for now. Okay, so let's fix that. So that's the baseline model, né? That's the mean absolute deviation. Mean absolute deviation for this specific model. Okay, let's put them together. So let's make this that a 4. You can see it's higher. Let's make that, oops, let's make that a 1. Also higher. Let's see. So if we make that, just make it a 1 there. You see, higher. Oh, this is lower. That's interesting, but it's okay. So let's go. So that should be a better model. If we do a 3 there, see then now it's also better. 8128. So it's 8. So well, if we make 0, no, it's worse. So if we make that a 2 there, let's quickly just play that. It's significantly worse. So it must go down. Let's make that 0. 82. So that's a small window of where it's better. Let's make that 02. See, it's worse now. So there's a small 1 or 2 variables where it's 0. But you see, you get the ideas that we're estimating these numbers to get the smallest mean, well, the smallest error, and that's what OLS actually tried to do, is to minimize the error. Okay, you can see this might be 1 or 2 small things, but 99% of the time, if you play around with this, you're going to get an error term bigger than the error term. And that basically means it's worse than that. So under this particular circumstances, these coefficients yields the smaller error term. But we know that this one is not statistically, that actually should be 0. So that actually should be 0. Okay, so although this is better, but if we remodel it, we'll most probably get different coefficients. So we can't just make that 0 and say, well, it's actually worse. Because if we exclude it, we'll have a different coefficient. So for example, okay, now we can do that on another day. Okay, so, but let's continue. So we can plot our graph. See, if it says hit run, then it means run it again. You can run it a couple of times. So what is this giving us? So this graph is giving us the fitted values and the residuals. And the residuals is our error term. So what that graph does is, it is this one. Let's quickly do that. And this one. Our error term. I shouldn't have done that, but let's quickly run it. It gives us this. Okay. However, it doesn't give this graph. It gives it in a what do you call this format again? Come on. So we're gonna go to file. Let's change start. It gives it us in what's it called now? Scatter format. There we go. See? It gives us the scatter format. Let me just quickly select data, error, edit, M2, P2, series name, P2, okay, that's fine. So let's have a look at it. It's come on. It's exactly the same, 0 to 50, 0 to 50, and then minus 40 to 80, minus 40 to 80, and it gives us this format. We can put a trend line there. Let's see. We put a trend line. Right. Let's do a polynomial trend line. There we go. And we're gonna go make it red and make it bigger. There we go. And I'm just gonna make it like, there we go. And now you have this. Okay. Here is a QQ. That's just test for normality of the residuals. And ideally you want the residuals to all lie there. So you can see there's this point here where it's struggling to account. And this is these high values here. You see all these high values you see here. It's close. Most of the values are concentrated around here. And as you go to the higher end of the rainfall, it becomes more tricky, and it's exactly the same what it says there. Okay, so you can see it's exactly the same. At the lower values, the actuals is clustered around, or the errors are clustered around the actual. So meaning the clusters of the errors are very little around the fitted. But as we go, as the rainfall increases, the errors starts increasing. That's exactly what we're showing there. Okay, let's plot it again. See what it now gives us. These values, so standardized and residuals versus leverage. Not too much of a hassle. Let's run it again. Let's see what it gives us now. Nope, that's basically that. Okay, we can also print the residuals, same things as we've done now, and we can also generate the residuals, same thing as what we've done now. Okay, so nothing different. There's the intercepts again, etc., etc. We can run it different. We can plot it. Let's just throw it away. This is basically what I've done here. That's a straight line, a linear function. So we can do that. We can say add a trend line, and we can say add a linear. And let's make that green. Make it also bigger. You see, it's basically the same thing. Oops. There we go. There's the green, which is exactly the same as that one there. Okay, we can do a histogram of the residuals. Looks normally distributed, but you can see there's those outliers there. There's those outliers, this high rainfall area. Or high rainfall, it cannot predict that high rainfall. So there's a lot of them there, you can see there. It's struggling to predict that. Box plot, QQ plot, we've already done that. And we just add a trend line to the QQ plot. We've done all of those sort of things. We can run it further. Wow, that's not. And run it. Those are all things that we've already calculated, we've run it, etc. But in general, it suggests that the model struggles to predict or to accurately estimate the actuals. It suggests there's, let's have a look. Okay, so there's a whole lot of visualizations that we can rely or that we can print or we can run to visually inspect our model. We can do it in Excel. Okay, you can do it in Excel by generating the estimate and then generating the error. And then we can do all sorts of calculations and graphs and things around that. Or we can do it in R itself. So that's all visual representations of our model. And the idea there is to visually analyze the fit of our model, the goodness of fit of our model. But coming back to my point, and this is the important point, is that we're still not sure about these coefficients. Because remember, how good or bad our model is dependent on these coefficients. The better these coefficients, the better our fitted model, i.e. the less our error, etc. etc. So we need to check these. We need to further analyze these coefficients. Okay. And so for that, we run a whole lot of tests. Okay. Now the test doesn't specifically tell us what the coefficient should be. It just tells us whether there may be a problem with those coefficients or not. It doesn't tell us. Okay, so those tests doesn't tell us whether that minus 3.38 should be minus 4, should be minus 2. No, it doesn't tell us that. It just tells us, it just gives us ideas or just gives us clues about the reliability and robustness of this test. It may suggest that there's a problem with this, and therefore, if there is test suggests there's a problem, here's going to be a problem, then we have to amend the regression, okay, so that we calculate the actual coefficients rather than these coefficients. So I hope that makes sense. Let me say it again. The tests that we're going to perform now, the aim of those tests are not to give us the actual value, the true value, the reliable, the robust value. It's just the test that we're going to perform now just tells us whether there may be a problem with these coefficients or not. The test will tell us, hang on, there's a problem. These coefficients may not be accurate. And that then tells us, listen, we must amend our model. We cannot use this model because these coefficients are wrong. Even if it's statistically significant, I said, that's a 0 or not, whether these coefficients are wrong and stuff. So that's the key thing that we're going to look at now. That minus 3 0.382. That's the thing that we now need to figure out. We know it's not 0, so that's done. But what is the actual value of that? Or could the value be problematic? Could this minus 3.382 be problematic? And therefore, we have to look at alternatives. And that's what we're going to look at now. And so first of all, we're doing the normality test of the residuals. Remember, we've generated the histogram of the residuals. And it looks in general fairly, we can copy this. And we can paste it. Oops, sorry. I can paste it as that. Okay, make it bigger. Remember, what we assume normality is a bell shape. Okay, it's not nice, but you can see there's a big number of values here. It's struggling to estimate this lasso. What we're saying, it's negatively skewed. Most of the values are on the negative side or on the small side, and it misses so this is negative skewed. Just check that it's not positive, it's negative skewed, yeah. Negative skewed. It's negative skewed. Okay, so is this skewness significant in terms of the normality of these errors? Is this skewness significant to detract from the normality of the errors? Okay, so let's have a look. Remember, we want the errors to be normal because then there's no outliers, etc., etc. So then the mean is is a good representation of the data. So we need to assess that. If it's normal, the chances are that this is good. So normality is good. Okay, normality is good. It lends credibility to this value. Non-normality suggests there's a problem with this value. Okay, so let's have a look for our normality test. We're going to test first we use the Jacob-Bahara test. LMS has a dotted sign, a residual. So we're going to test for normality in the residuals of our regression. Let's run it and see what we get. There's our output. What is the null hypothesis? The null hypothesis is that skewness and kurtosis equal to 0, meaning normality. So here we want to accept the null hypothesis. The null hypothesis suggests that variables, our error is normally distributed. There's no skewness or kurtosis. Okay, you guys can read up on those two items. The one is left and right. Skewness is left and right. Kurtosis is up and down. Is it too narrow? Is it too flat? Skewness is it to the left, or it's negative or positive skewness? We've already said there's a hint of negative skewness, and it indeed suggests it is not normally distributed. Because here we're rejecting the null hypothesis because the p is very small. Remember, small p, alternative. High p, null hypothesis. Let's look at Shapiro test. It's a different test. Let's look at that test. The null hypothesis, residuals are normally distributed. Again, very small, p-value very small. So in both cases, we are rejecting the null hypothesis. We are rejecting the null hypothesis. Well, in most cases, it will be very good. You'll be very happy. But in this case, we don't want to reject the null hypothesis because the null hypothesis is that the data is, or not the data, the errors are normally distributed. So in this case, there's a problem with normality. Our errors are not normally distributed. And that's problematic in that the model, that coefficients cannot capture the outliers. And we've already spoken to you about that. The outliers are still captured in the error, not in the estimate, not in the model, as you can see here. Then, so that's two tests that we're performing, normality. Then we're looking at the Durbin-Watson test. Okay, let's run the Durbin-Watson test. What is the null hypothesis? The errors are serially uncorrelated. It tells us here, alternative, the true autocorrelation is greater than 0. So again, here, our null hypothesis, the errors are uncorrelated, meaning there is no serial autocorrelation in the errors. Now, that's a good thing. That's what we want. We don't want the errors to be serially correlated. We want them to be randomly distributed. Now, if you just look at the errors, there's the errors. Okay, you can see it's randomly distributed. There's outliers. That's the normality issue. That's normality. But you can see it's not serially correlated, meaning 10, 10, 10, 10, or 5, 5, 6, 7, 8, 9, 10, or there's no pattern in the numbers. It is random. And that's good. That's very good. And the p-value is bigger than 0.05. Okay. The one is close to 2. So that's good. It's bigger than 0.05. So therefore, we accept the null hypothesis. What's a null hypothesis? Errors don't have any correlation. So that's good. That's very, very good. So that's excellent. Now, after two disappointing tests for autocorrelate, for normality, This one is important. It tests for serial correlation or autocorrelation in the errors, and there's no sense of it. That's good. So we can also test for homoscedasticity or heteroscedasticity, which is opposite. What do we want? We want homoscedasticity. Real residuals have a constant variance. Now, just quickly, when we look at that, does it look like the errors have a constant variance? Nope, doesn't really look like it, huh? What would be a constant variance? Constant variance, let me quickly do this one. Let me just put this forward. This is a constant variance. You can see the variance from the mean. If we assume 25 is the mean, it's constant variance of the mean. So that's what we mean by the variance. It's a constant, it's a zero or the mean, whatever the mean is, and there's constant variance around this mean, meaning the differences around the mean is all exactly the same, either 5 this side or 5 that side, 5 this side, 5 that side, 5 this side, 5 that side, whatever the case might be. Okay? It doesn't look like it. It doesn't look like it. So let's quickly run that and see what the results look at. Oops, sorry. Hey, come on. And you can see the p-value is very, very small, and therefore we reject the null hypothesis and we accept the alternative residuals don't have a constant variance. And I just showed you that. Visually, I just showed you that the errors don't have a constant variance. And that basically also has to do with normality. Okay, if it's not normal, most probably it will not have a constant variance because of those outliers and. So these two things go hand in hand. So there's heteroscedasticity issues. Okay, there's heteroscedasticity issue. It's missing something that's declaring or that's capturing the outliers or the high values. There's something missing in the model that prohibits the model from accurately capturing the high rainfall numbers. And that basically brings us to this test, the reset test, which is testing exactly what I'm saying now. And the p-value is very, very small. The null hypothesis is that the model has no omitted variables. And again, we're rejecting it, meaning the model has omitted variables. It's exactly what we're saying there. If your model suffers heteroscedasticity issues, then it basically means there's something missing. The model struggles to capture some fundamental stuff. And that fundamental stuff is causing the heteroscedasticity, non-normality, etc., etc. It's problematic in that the model, that coefficients are not good. Those coefficients don't capture the essence of the variable, the dependent variable, in this case rainfall. The model cannot accurately predict these high rainfall periods. If it's just one outlier, then it's fine. But here there's lots of high rainfall and the model cannot, because it has a non-constant variance, it has outliers, it cannot capture those outliers, etc., etc. So all these tests, okay, they're all basically related to one another. So yeah, so model has no omitted variables. Let's look at the fifth test, and that's very much multicollinearity. Okay, there's only two, so there we go, multicollinearity, so we're testing it. So that basically, only because it's only two, and it indicates whether these things are actually the same variable. Correlation, which is 0.58. Remember, we want our independent variables to have nothing to do with them, to not be the same. It's like hours and weeks. So basically the same thing. Why would you have hours and weeks in the regression? Because they're the same thing, it's time. So you don't want these two things to be the same, because it just skews your coefficient. Rather than having both of this captured by this coefficient, they now have it captured in two different coefficients, meaning the coefficients doesn't work. So for example, if I do this, for example, if I leave W out and then run it, you can see the coefficients are now very different. There's a 104,428. Okay, 104, so that's different. That's minus 3.38, and that's minus 3.3. That's not too different. Yeah, but still, you can see if I make that zeros, it's quite a bit different. So that 0.30 is actually, if these two, if that plus wind, if they are highly correlated, then that, if I run it again, oops, sorry. If I run it again, you see there's the 0.38 and there's the 0.3. See, it's different. So basically, what we're saying, if this W and maximum if they are correlated, then that value there is wrong, because the value actually should be that, given that this value is 0. So if we say this value is 0, then that value cannot be minus 3.38. It actually should be minus 3, because these two things in reality is exactly the same thing. So we have to test for multicollinearity, meaning multicollinearity is when these things are related. And we test for it by using the fifth test, which indicates some sort of collinearity between the two. And we can calculate the correlation between the two, which is 0.6. It's not high correlation, but ideally you want it to be 0. This one you want to be 1. You don't want any correlation, because if they are related, they will affect one another's, the coefficient will be affected, and therefore the coefficient will not be accurate and robust. And then we have this that we do, and we'll go through that as well. So there's a whole lot of tests that we're doing. And the reason why and you can see basically it only passes this test. That's the only test that this specific model or regression passes, is the fact that the errors are not correlated. That's the only thing that it passes. The rest, it all fails because of basically two facts. One is that you can't have max and W in the same, maximum temperature, wind in the same regression, because they're fundamentally the same thing. And two is there's some variables, there's omitted variables. There's some observed or unobserved variable that we need to include that can capture those outliers. And so what we now need to do is take W out and then add variables that are not correlated with max, okay, but indeed can capture these high rainfall, clouds, pressure. I don't know what we can play around with it, okay. But because these ones, so what the model is telling us is that this 3.38, although not 0, which is good, is not minus 3.382. That is rubbish. That's wrong. That should be something else. And the reason why this is wrong is because of heteroscedasticity, meaning x and the two x's are correlated, and omitted variables. There's something that we not included. So now the heteroscedasticity is easy. We just drop W. The omitted variables are not easy, because we now need to go and do our research. What else can influence rain? Because that is what we now need to bring into our regression. Okay. So before I go into more detail on these ones, let's park there for now. yeah, I hope you're still following. I hope it's still making sense. If there's anything that I'm missing or you want me to further go into, please let me know. And yeah, thanks for watching, thanks for joining, and thanks for watching. And please do like, subscribe, share this video, watch them full time. I need those hours, please. I need those hours. Watch out for the next one. Most probably will land tomorrow. If I have time, I will land tomorrow. Maybe just one more on regression, and then I want to do one or two more on general equilibrium and see where we focus. I also would like to do one on linear programming, etc., etc. So let's see where we go. There's no rush. There's no I have to do this, I have to do it. We play it by ear. Okay. So yeah, thanks again, and I'll see you on the other side.